Share screen. Screen 2. Share. Yeah, it should be good. And then if you want to go next, so select that.
So these two.
Left and right. Yep.
Okay.
Right.
Time.
Mm-hmm. Yeah. Right.
Good. Well, let's get going today. So I have pleasure filling in for Rem for a couple of lectures here and a couple of lectures a little bit later on. My topic today is going to talk about gas chromatography. And then later on, I'll talk about mass spectrometry. So those two topics I've spent most of my life with, and so pretty comfortable with them. In terms of what do you call it? They're different names, different places. Typically, call it GC, gas chromatography, but some people talk about GLC, and that would imply gas liquid chromatography. There's no liquid in this technique, and so it seems like a misnomer. The HRGC is a high resolution GC. They're all high resolution GCs today. So anyway, we get by with just calling them the GC. So I'm going to kind of go through the hardware. What is it here that's we're working with? So chromatography, how does the chromatography happen in this process? What's the mobile phase, stationary phase, and so on? How do we do it well? Hopefully do it the best. What problems do we run into? And then give you 3 examples of applications of this technique. So from a history standpoint, maybe Pam's gone through histories. Something like 1850 was the first use of chromatography. Separation of pigments by pigments came up around 1906. Gas chromatography came in 1941. That's when the first paper was published on this technique and was a theoretical treatment. The first actual GC came about 1952. At that point, they were collecting the gas coming out of the gas chromatograph, condensing it and titrating it. Not what you'd call a simple technique. So 1954 was when a detector came at the end that samples could come out and you'd actually get a peak that represented what just came out. So we could probably say that 1954 is when gas chromatography truly started. The applications today in our field are immense. Fatty acids, I think that's what you're doing in class, is looking at fatty acids. That was one of the first uses of it. Cholesterol, normal gases, whether it's oxygen and oxygen package or nitrogen packaging, whatever. Solvent purity, water, alcohol, sugars, amino acids, vitamins, pesticides, food additives. We can go on down through the list. There's just an immense number of compounds that are measured by using gas chromatography. In some cases, you kind of look at them and say, well, this is a gas method. Are we really looking at sugars? Are sugars volatile? Are we going to get them into a gas phase? If we make a derivative of them, make a triethylsilyl derivative, hexamethyl disilazine, something like that, we can make sugars volatile. We can make amino acids volatile. We can make peptides volatile and do a separation on technique. So the technique just depends upon something becoming volatile. Oftentimes, if we have to make it volatile, oftentimes there's a better technique, and that's called liquid chromatography, right? We don't worry about changing it into a gas for our separation. The process is really simple. If we're dealing with vapors and compounds that are volatile at ambient, fine. We can just take a gas-tight syringe and drop some of the gases over that sample and inject the sample in that manner. So we could do a vapor injection. But most of the time, we are dealing with things that aren't a gas at ambient. And so we have to vaporize it one way or another. And so we use techniques, and I'll show you what they are, go through them as we go through them. But okay, either a volatile material, it's in the gas phase, it's moving with the gas phase, that's the mobile phase, or we make it volatile so it moves. It passes through a column like liquid chromatography, most other techniques. That's where the separation occurs. And so we've got a mobile phase, that's a gas, and then we have a stationary phase that's on the inside of a column. And again, you'll get an appreciation for those columns, the length of them, their composition, and so on. Of course, that's the heart of the machine. What is that column that's in there? That's where our separation occurs. And we have many different types of detectors. There are some workhorses that I'll mention, and a couple that are just more or less, they're known, but they don't find use today very well. So this is what we call the hardware, kind of a simple diagram of a gas chromatograph, but what does it involve? We need a mobile phase. So we buy a cylinder, could be a cylinder of nitrogen, hydrogen, helium. So we have a gas here. We need some way to control that flow, so we have a flow controller. We need a way to inject our sample or get our sample into this column so we can get our separation here. And that's typically through a polymer septum up here that keeps the gas from going up. So we take a syringe, pierce that, vaporize it at high temperature, and it goes through the column, travels along the mobile phase, interacting as it goes along, and hopefully not being separating our compounds. There has to be some kind of a detector. So, okay, we should draw some peaks, or it draws some peaks for us. And of course, the peaks represent in quantity the material we want to measure. And waste, I guess that's the effluent that comes off of the gas chromatograph, but that's simply burned compounds. How's that? Not too interesting. So those are the major parts. This is now a little more detail on that diagram. So here we have our mobile phase, and a couple other cylinders here, say why, but here's the mobile phase. Shut off on here, some kind of a filter, flow controller. Now that goes down into the system, goes right down into the column, through the column, comes out, gets detected, and we draw a chromatogram. So a little more parts to it. Why do we have these two cylinders, an air cylinder and hydrogen? That looks like a flame, doesn't it? We can make that burn. So this is for our detector. When our compounds come out of this column, this is where the hydrogen and air are mixed with it, and our compounds are burned. They're burned in a flame. Burning induces ionization. We get bits and pieces of ions that come off this flame. And so basically, we're monitoring the ions that are coming out of that flame in this process. So little more detail on that. So did I go the right direction or the wrong direction? I went the wrong direction. Okay. Source of our mobile phase. This one's kind of amusing to me. It's amusing to me because I've probably got 8 or 9 phone calls about this in the last 3 weeks. Mobile phase. So over here, what's this carrier gas? Traditionally, it's been helium. It's almost impossible to get helium these days. There's a real shortage of helium. And so people start looking at helium. So that's about $180 a tank, $200 a tank. I could get some other gas much cheaper. For example, hydrogen. And actually, you'll see later on where hydrogen is a better choice than helium. But traditionally, we use helium. It's inert, it's pure, it's clean. It really works well. But if you can't get it, the questions that I've got, I can't get helium for my gas chromatograph. What can I use? I usually say hydrogen. They say, no, hydrogen will blow up. It's really hard to make hydrogen blow up when it comes right down to it. You'll have to have exactly the right mixture of air and hydrogen to make it ignite. That's what our detector is. And sometimes we have a heck of a time. We don't get the right blend of gases to make it even burn, to say nothing about blow up. And so they usually tell them, no, hydrogen's fine. And then they say, is there something else we could use? We could use nitrogen. but that's not very good choice. So I tell them, you got a choice, do something good, cheaper, cleaner, better, not really explosive that comes right down to it, or nitrogen. So that's our mobile phase, and right now, most people are using hydrogen, especially since, like I say, helium is come in such a short supply. And of course, we need the gases over here. So we need our air and hydrogen as again, hydrogen shows up here. Carrier gas is in our flame ionization detector. So our detectors may require a special gas as well. And so the flame requires air and hydrogen. Well, some of the other detectors that we have that we'll go through, we can use other gases. We must have other gases. But anyway, for our practical purposes, we get along basically with air and hydrogen is a carrier gas. So those are the cylinders we need connected to it, and for those reasons. We have to, we've got tanks with a couple thousand PSI pressure inside of them. Okay, we need to control the flow of gas. So we need to reduce that pressure. We need to control the flow of these gases going into the gas chromatograph. So obviously that requires a flow regulator of some kind or another. So we've got our column, we've got this gas going through it. We have to control that carrier gas mobility. And so we need some kind of flow regulator. And this is where we get in trouble sometimes too, that some people will come from different fields, or they'll say, gosh, regulator, you got a very expensive regulator on there. Can't we get along with a cheaper regulator? I go down to the welding store to get one for $50. You're going to charge me $300 for one for this instrument. So it does the same thing, but these regulators have to be clean. We talk about femtograms, sensitivity. If those pressure regulators are not clean, if everything inside is not inert, you start determining what's in the regulator, not what's in your sample. So when you get a regulator, you make sure that it is stainless steel and it's approved for this purpose. These are sensitive instruments, these regulators too. There's a number of flows you have to control, and these are handled with kids' gloves in terms of how you turn them, the tightness, and so on. So you do treat them as precision instruments. So flow regulators. Like I said, you have to get your sample into this gas. So we've got our carrier gas coming in, our mobile phase coming in. We got to get our sample there somehow into that flow so we can get our separation in our polymer. And that's done in what we call the injection port. So here comes our hydrogen. That's our mobile phase coming in. The hydrogen comes into what we call the injection port. This is a heated chamber. We'll typically run 250 degrees centigrade. If our compound isn't volatile, we squirt it in there. It's volatile, you hold it, or it's not going to go anywhere. So you can put liquid samples in and you volatilize them, vaporize them here so they get into the column. So your carrier gas is coming in here. Some portion of it goes down here into our column and so on. There's also an element here, carrier gas comes on here, and some portion goes out a split. And you'll see why we have this a little bit later on. There's also then a bit of purge gas. There's some gas that comes right across here and goes right out into our room. And the problem is, this is a little rubber septum. It's not rubber, but it's a polymer septum. We've got to put a syringe down into here. So we need something we can put a syringe through. And so this polymer can give off materials. It's going to be 250 centigrade. It can give off volatiles. It can decompose. And so anything that's decomposing up here comes down here, but then goes swept off here. So this is basically, this purge gas is keeping the system clean. So anything that degrades up here can't contaminate our system. We put our syringe down here, we make our injection, and then some part of it, like I say, goes out again. The rest of it goes into the mobile phase. I should have brought a capillary column with me. I'll bring it next time. I hope some of you maybe have already seen a gas chromatograph, seen some of the columns that you use. The columns are about 2.25 millimeters, 2.25 millimeters in diameter. They're tiny, very tiny, very slow rates of gas flow or slow volumes of gas. And so we've got to do something with all this gas that's coming in. And most of that simply goes out of that. And some of it with your sample is carried into your column where you do your separation, your analytical work. Many versions of that injection port. I showed you the most common one. That's a split injection port. The column is so tiny, it can't manage much material. You have to work with very, very low concentrations, or you just kind of swamp it, you flood it. And so that's why we may go in with 50 mils per minute gas, put our sample in it, and only take out 1 or 2 mils that we actually analyze out of that 50. And so that's our split injection port. We simply can't manage those flows. We can't manage the concentrations. We get rid of most of it through a split and put only a small amount into your detector. Split less is a system that's really a little different. I think I get to show you that a little bit later on. So I won't. But I put all material injected goes into the column. Well, that's not exactly right. So I'll kind of put it in parentheses why. But they're splitless. On columns, we do a cold injection. Maybe your compounds degrade on heating. Oh, that doesn't do very much good putting them into 200-degree centigrade injection port. They break right down. So we can do a cold injection. And I'll show you again how this system works. There's also some that are program temperature. Your detector is cold, you make your injection, and then it warms up. It may go 100 degrees per second. It's going to warm up and quickly vaporize the sample. So program temperature. Sensitive materials, they volatilize before they decompose as it's being heated. Large volume. Normally we work with a 10 microliter syringe. That's what our sample is, and not very commonly deal with 1 microliter injection. But there are systems that we can put up to 1 milliliter into that injection port. So you're dealing with something that's a very, very low concentration. Well, you can inject more. There's tricks to go about this, designs that go about this. So this is really, I was going to say the heart. It isn't the heart, but it is the beginning of the system. And it's a place where oftentimes we have problems with our system, where things break, things don't work quite right. And so we spend a little more time on the injection port than we might anticipate. If all it does is vaporize our sample, okay, and split it, that's good. But there are some catches to it. I think I deal with that in the end when I talk about problems. So, but this gives you an idea. Maybe got 54 mils per minute of hydrogen or helium coming into the system. You make your injection here. This expands. Some portion of it goes down the column and out this way. The majority of it actually expands, comes around here, and goes out our split bed. So if we have 54 mils per minute coming in, 3 mils come right across here, just in case there's any crap coming out of here we don't want to get in our system. Garbage, garbage, goes out this direction. Then 51 mils come down here. 1 mil goes into our column. 1 mil per minute goes into our column. Pretty slow flow rate. And the rest of it comes out here, 50 mils per minute. So that's a little bit more of that injection port. And there's various controls. You can control your column pressure, control that split ratio. That's a 1:50 split, approximately. So 1/50th of your sample. I could go in with 20 mils per minute up here and have a 1:20 split. So you can see I can change my split ratio, how much gets dumped, vented, and how much actually goes into the instrument. And that's controlled somewhat by the concentration of our sample. Do we really need more material on our column, or don't we? This is the splitless one with a little more detail. 54 mils per minute coming in here. 1 mil per minute goes into our column. The rest of it is actually going to come out and go off this vent as well. But the way it works is, this is kind of our initial setup. And So we're actually be putting some flow down here and a buildup here. And then we split out. So instead of having it come immediately, we give it a little bit of time to build up, and come down here. So we're actually putting a large amount of sample on here before then we split and get rid of the material that's in there. So different detectors, basically what do you want to accomplish? If you got a lot of material, you use one injection port. If you don't have much material, you use a different kind. If your material is heat sensitive, that's going to decompose at 200 degrees centigrade, your injection port temperature, you use also a different system. In this system, we could use an on-column injection. So we've got a syringe here, and a really long needle. And so in this case, you've got your carrier gas coming in here, that gets your column, and keeps everything going on here. But you've got a syringe with a long needle. You kind of put it down here, it goes to this valve, goes down into the column, down into the column, just for the gas chromatographic ovens. So it can be fairly cool down here. So none of this is heated, but we've got compounds that thermally decompose. A long syringe, and you have a cold injection port, and you put your sample down here, and it goes on its merry way for separation. So your first question, kind of always, is what kind of injection port do you use? What kind do you need? Is your sample heat sensitive? Do you have much material? Is it high concentration, low concentration? So a number of questions go into choosing your injection port. Probably 99% of the work is done with a split system. That's kind of the one that works. It's a really sensitive technique. It works well. So of the three that I showed you in detail, the split is by far most common. Columns. I used to have a packed column. I should go take a look in the lab and see if I can find one. They used to be about the size of a pencil in terms of diameter, and they would maybe be 10 feet long. Very commonly, they were glass. So you kind of had this glass piece coming in, then a loop, and then going to the detector. And big column, say, size of your finger, they were packed with a granular material. They were packed with what your phase, your compounds would, let's say, interact with. They weren't very efficient. They were the first thing we had. They did the job for probably 20 years, and they've been replaced. So you have to go to the archives, the antique show, to see any of these glass columns around before. What we have today are called open tubular columns. They're by far the most common. Have any of you done the GC lab yet, or is that coming up yet? No, it's coming up. It's okay, it's coming up. So you're going to get to take a look at this. This is about 30-meter long column. We've got 30 meters of separation power taking place here. And that's the 0.25 millimeter diameter. So it is really tiny column. On the inside of that column is a layer of adsorbent. So that's your stationary phase. And that will probably be 0.25 microns in thickness. So exceedingly thin film, very, very small diameter. These work very much towards efficiency and separation. Thin films, small diameters are what give us amazing resolution. So this is by far the workhorse. Another kind of capillary column, and it's called a porous layer open tubular. So these columns will actually be coated on the inside. So there'd be they might be a 0.53 millimeter. So from 0.25 to double that. So about twice as big in diameter. And then there's a coating on the inside. And that coating is then what you need your separation with, is the coating on the side. So that works for some types of materials, especially if you want to monitor the oxygen content in a package. Okay, measuring separation, oxygen, nitrogen, and so on, that doesn't work well on this type of a column. We don't have any good phases that are selected for oxygen versus, CO2 or hydrogen, whatever. And so we kind of put in different phase inside. So these are mainly for gases, to work with gases. So what are our columns? They're generally a fused silica. You can take them and tie them or not. Try that with most classes. Most classes really don't like to tie in knots. So the fact that they're the closest you can get to 100% pure glass. Normal glass that we come in contact with, there's other things added to it to make it stand temperature shocks or all kinds of different effects. But this is absolutely 99.9999% silicon. So there's nothing that interacts except silicon with your compound. They're strong and, like I said, inert. The diameters can range from 0.1 millimeter to 0.53. That's inside diameter. 0.25 is really a workhorse. That's generally what we have in our laboratory, 0.25 millimeters. I'll talk about why we pick 0.25 a little bit later. Let's kind of take the 0.25 to the workhorse. Length 1 meter to 60 meters. So you can actually have just columns long enough to go from this part of the gas matter after that, connect the detector to the injection port. They can be that short, or they can be up to 60 meters. They can go longer, but there's no point in going beyond 60 meters. It takes a long time to get your analysis. If you have to go to 60 meters, you're wasting your time. You should find a different way to do it. So our normal length is 30 meters. So if we look for our column, it's going to have 0.25 millimeter diameter, 30 meters in length. That coating inside can be a very thin coating or a very thick coating. And that's capacity. How much material can I put in? What's the concentration? If I have a lot of material in my syringe, in my injection, I might use a thick film. If I have a little material, I might use a thin film. So kind of standard column. If you walk through our lab, we probably have 50 columns. They all fall really close to that, 0.25, and 30 meters. It's kind of funny. I'm old enough, as you might guess, to have lived through the evolution of gas chromatography. At one time, we had over 200 different coatings that you could put inside these packed columns. So they were granular material with different coatings on them. At one time, I say we had over 200. They were very specific. You had to have a coating that would work just for these two materials, these two separations. They weren't generally good beyond some selective power. And so that 200 is kind of boiled down to 1, 2, 3, 4, 5, 6, 7, 9 coatings. So this is the materials put inside of this silica column. Dimethyl polysiloxane is really the true workhorse of it, of this field. That's number one by far. This puts a little more polar nature to it. And so a little bit of polarity helps. This is very, very nonpolar. And so if you're working with nonpolar substances, you want to have them interact with this coating, you use this nonpolar material. A little bit of polarity, we tend to use this. If it's a fair amount of polarity, then we're down here at our modified polyethylene glycol. So literally, we get a lot by in our lab with 1, 2, 3 of these materials. And they typically do the job for you. So gone from 200 to 10 or so. You go from 10 down to 3, practically speaking. There's some, unique separations. You might find a different column, but it's really, really rare. This tends to take care of it for us. How do we know what column to use? So we've got 3 different choices, 3 different types of column. How do we know which one to use? Should it be a nonpolar? Should it be partially polar? Called oftentimes semi-polar, or should it be polar? And this is where we find the literature's like handy. Probably my favorite website is called PubChem. And so it gives a lot of information about the chemical properties of pure materials. So again, I can look up most of the chemicals I'm interested in, and I can find several pages about chemical properties. And one of the things they give is separation by gas chromatography of that pure chemical. I'm a flavor chemist, so I'm interested in things like benzaldehyde. Benzaldehyde is maraschino cherry. If you go taste a maraschino cherry on anything, and you get that, what's oftentimes cherry, a red cherry, It's due to one chemical, benzaldehyde. I may wonder, okay, I got a separation. I want to separate my cherry flavor from something else, my component. What column should I use? I can look up and say, what's my separating ability of benzaldehyde? What's the best column for it? And then other things I think are in there as well. So there's a nice reference here of listing the chromatographic properties on different columns, these three different columns. There, what they list that's really useful to us, we call linear retention indices. That gives you retention data for a given compound on one of these columns. It can be also called Kovacs indices. That was Professor Kovacs was the person who drew this up and says, hey, let's have some way of standardizing, some way of categorizing elution of compounds in gas chromatography. So this is the inventor's name, and this is the generic of that name of the system. So if we're interested in what column to use, we can certainly look up if we know what we want to separate. We can look up the retention index. Where does this elute on this column? Next one, where does it elute, and so on. And you can pick a column. And when you make an injection of 5 compounds, you can know exactly, I know what this is. That's the first one, has the lowest Kovacs index, and the second Kovacs index. And so it's really, really helpful information about chromatography separation. But also, a lot of things have been done in this world. A lot of things have been published. And so, of course, if you're doing a separation, you also go to literature and say, what did somebody else use? They'll typically give you a chromatogram, see how nice this is. So, okay, you can learn from what somebody else has published. If you're in a company or maybe in the university, you can say or ask one of your colleagues, have we ever done the separation? Oh, what did you use? Again, looking at published information in-house. So in show work. If you don't find the compound one of these ways, I'll be amazed. Okay. There's some things maybe that haven't been cataloged yet, but boy, most of the things you've got. If you can't find it anywhere, that goes into intuition. So you have a certain chemical structure, and you know what the chemical structure is. Okay, you look at that structure. Is there a column that's related to that structure? Or is there a similar structure in the internal of a column? So that helps you. Just use intuition. Use the same type of material, polarity, whatever, as you wish to separate. No idea. Don't have the foggiest idea. You don't know what the compound is. You don't know where it came from. You know nothing about it. And you kind of go through whatever information you can get. I've had people bring some drywall from their house into the lab and say, Carrie, my drywall stinks. My house stinks. Can you help me? Well, where do you start with that? I would have no idea. What did I do? You start with a nonpolar column. That nonpolar column is by far the most durable. It's hard to ruin it. And so if you're running something you don't have any idea what it is, you don't want to ruin that column. It's about a $300, $400 column. So you pick a good nonpolar column and say, let's take a look. And if that doesn't give you a separation, okay, then we change to polar. But no idea. Just take your OV1, your whatever, SE30 that you saw before, and that's what you use. There are a few techniques that are as good at separation as gas chromatography. This field was probably mature in terms of its ability to separate about 1980. So we're not going to get any advances in terms of improved sensitivity or separation, let's put it that way. It's mature. We've reached, like I say, theoretical max. And why is this number one? Well, it's number two. There's one other chromatography method that's superior. But it's, if you think about LC being here, liquid chromatography, gas chromatography someplace on the roof looking down at LC. I look at liquid chromatography Stone Age. Don't tell Pamela shut that. She likes LC. So again, we kind of oh yeah, we've got the four different we have four different techniques or principles of separation. working for us in gas chromatography. We can take advantage of adsorption. Is our stationary phase similar to the compound that we want to separate? That's how we'll choose them. Is there affinity back and forth? So we take advantage of this affinity between the stationary phase and your compound. Molecular exclusion is an interesting technique as well. And that's so certain sizes fit into certain slots and certain holes. And so you can make use of this. That's what we use for permanent gases. I want to separate oxygen, nitrogen, hydrogen, and so on. I set them based on molecular size. So there's some absorption, but molecular exclusion is number one in terms of separating for that purpose. I can also take advantage of partitioning. We've got this coating inside of our column. Is my material want to dissolve in that internal coating? Is it going to dissolve, come back out, dissolve, come back out, move down the columns. So in partition chromatography, we also have volatility. We take advantage of our boiling point differences between compounds. We typically start our gas chromatograph out around 50 degrees centigrade, and we program it up to 250 degrees centigrade. So at 50 degrees centigrade, things that aren't very volatile, they're not going anywhere. As we jack that up, oh, now I want to get out and get going. Okay, now I want to get out and get going. So in gas chromatography, we take advantage oftentimes of multiple combinations of these basic chromatographic principles to accomplish our separation. And that's why it is really such a good technique. Not just one type of chromatography, but multiple types of chromatography in one column, in one particular run. These are our three columns that I've mentioned before. I don't know that I gave you names for them before. The nonpolar is typically a DB1. Why is it a DB1? I have no idea. But that's a very, very nonpolar. It's a silica phase. Nothing on there polar whatsoever. Here we add a little bit of polar materials into that coating. And here's our polar, and that's an ester type column. And why DB1? It could be OV1. Every company, Hewlett Packard, they give it their own number. So they may have a Hewlett Packard HP1. Another company may call it an OV1. But if you're looking at gas chromatographic column and has a one after it, that's your nonpolar by that specific company. So that's just something to pay attention. If you come across the columns and you see something else, some other name for it or number on it, what's that? Is the company name. But they're exactly the same compound, same columns across manufacturers. Column ovens. Well, okay, we're taking advantage of boiling point, as I said, volatility. How are we going to drive our volatiles out of the stationary phase into that mobile phase and be moving down the road by heating it? Higher the temperature, the more volatile it is, more it'll move into that phase getting out of there. And so we take advantage of our column temperature. Our columns sit in an oven. Let's say we'll start them off maybe 50 degrees centigrade, program them to go up at maybe 3-4 degrees centigrade per minute. So that column is ramping up. It's forcing more things out of that liquid coating. That shouldn't call it liquid coating. It's not liquid. So that coating, column coating inside, does that work? Okay. So we're forcing it out of that coating into that gas moving down this merry way. And so we do take advantage of that boiling point volatility. And these ovens can be run from minus 60 degrees up to 400 degrees centigrade. So I talk about 50 degrees centigrade. That's kind of where we work for types of things we look at. But if you're looking at some materials that are exceedingly volatile, you may be looking at much, much lower temperatures. So you get down to minus 60. And again, in foods, volatile compounds, things we're going to run in the gas chromatograph, we never have to go up here. 200, 250 centigrade typically takes care of it. But that oven is designed for a great deal of flexibility. Detectors. What are detectors for? I could ask that as a tough question, right? They're for detecting things. Okay. It's column. It's in this gas, right? So here, mobile phase is moving compounds are in that. We got to detect it. We have some way to measure it. And so we need to, and what we're going to do is going to change the quantity of some analytes into an electronic signal. So we can have a chart down here. Oh, here's our solvent, tons of solvent, right off scale. Oh, finally got rid of that. It's eluted off the column. None of it left in the column. Oh, here's our first compound separation, our second. Nothing going on. Here's third, fourth, and so on. And so we need to have some kind of a signal that we can turn into a concentration. And that's what our detector does. So sure, basically we're looking for amount. Many types of detectors varying in sensitivity and selectivity. And so we'll hit up kind of the major ones. We'll spend more time with those that are really major, less time with those that are lesser major. How's that? This is one type of detector. It's called the thermal conductivity detector. In that case, what we have basically is we've got our gas flow through, so our mobile phase is coming through here. This is our gas molecules coming along here. This is heated, so we've kind of got electrical current heating this, and we've got a device that measures current, electrical current going through here. And this kind of equilibrium. This is cooling it. It's cooling it, changes resistance, changes electrical flows. And now if we put an analyte in there, so we've got analyte coming off our column. We don't have just this cooling our columns for cooling this filling. We have a different gas composition. The different gas will cool this differently. And so we're measuring what's the difference in cooling of this particular filament here. The neat thing is about it, and that probably comes up on the next slide, is that this detector will measure anything other than the carrier gas. If you've got hydrogen as carrier gas, anything other than hydrogen, it's going to measure for you because of different cooling. But you want to measure water, doing moisture content by gas chromatography, you can do that. Measures water. Water is different than the carrier gas. Changes the cooling. So basically, any material it is sensitive to. It's a universal detector, is what it's called. And so specificity, like I say, it'll detect virtually anything. Universal detector. Sensitivity to 10 to the minus 7th grams per second. 10 to the minus 7th grams per second coming out of that column. Would you say 10 to the minus 7th? Would you say that's kind of good? Is that kind of mediocre? What would you think? Would you be happy with that? It's poor. Ah, darn it! I had that on the slide. No fair. It sounds pretty good, and it isn't bad. This isn't bucket chemistry. You're not carrying it around, but it's still very poor in comparison to the other detectors you'll see. We're down to 10 to the minus 14th grams in some cases. You start drawing circles out, and okay, you start seeing sensitivity of this instrument. Also, the linear dynamic range. You want to relate this electronic signal back to concentration. That's always your goal. And if something isn't linear, how do you do that? And so if your concentration in your samples changes by 10,000 fold, it's no longer linear. And so it's not really very good in that sense. The other detectors, you can change it by million fold and you get still linear response. So it's not bad, but it's not good in comparison to the other alternatives. This is the workhorse of detectors. And so here's our column comes in here. Last few the column coming here. We have our hydrogen in here. And we have air coming in someplace else. And we got air coming in someplace else. So we'll put it in here. What the heck? So we then ignite that hydrogen flame. So we've actually got a flame burner inside. And as compounds elute out of your column, they go through that flame. As they go through the flame, they get burned. As they burn, they liberate ions. Those ions are detected here. So this changes the electrical potential here. So we look at the electrical potential here and how it's changed by what's being burned in that flame. And that's one of our most useful detectors. I would guess somewhere 90% of all gas chromatography uses this type of detector. Very, very broad. If it'll burn, most organics, yep, you're going to get a signal from it. So specificity looks for most organics. Well, we're not down with that other detector. The 10 to the minus 12 grams per second. If there's 10 to the minus 12 grams material coming out of that column, going into that detector per second, you're going to get a signal for it. And so it's really good for organic materials. So again, in foods, what I would look for a lot of organic materials, linear range, 1 million to 10 million fold. Concentration can change that much and you still get a linear response, which is absolutely essential. There are some modifications of that, but they're really special detectors. We'll stay with the mainstream. So this is the workhorse, absolutely the workhorse of the industry. We're seeing less use of electron capture. Here again, we've got our column coming here. We've got a makeup gas, a little larger flow of gas. What we have is we actually have a nickel-63 radioactive detector. So the inside of it is radioactive. As it gives off electrons, those electrons are measured here. So we get electrical signal between the wall here. As compounds, organic compounds we want to measure come up here, the organic molecules absorb the electrons. So the current decreases. So we normally have electrical current between the two. But anything that traps electrons, it basically reduces that signal. So again, it's really a nice sensitive detector. There's a fair amount of specificity to it. Hydrogen flame, anything organic. Okay, electron capture, it's really different requirements. Halogens absorb electrons. Conjugated carbonyls trap electrons, nitriles, and a few others, but not many. So it found its use in looking at pesticides, herbicides primarily, because they were chlorinated compounds very commonly. And so if you're looking for anything that's conjugated carbonyls, so on down the line here, 10 to the minus 14 grams per second. So again, very good sensitivity. Linear range, not so hot, but again, selective, sensitive. Radioactive detectors have definite temperature limits. Yeah, you don't want to boil off that nickel coating into the room. It's radioactive. So, okay, bad idea. Chemiluminescence, I think we probably can get through these next two. In specific detectors, in these cases, we're using a detector that's light sensitive. It looks for, as we burn compounds, I don't know if you've been to the Science Museum, but maybe if you did soils or something, if you've seen them burning it and watching as elements, different elements come through, it changes the flame, the color of the flame. And so you've got a detector that's actually monitoring the flame that comes off the burning of the column. And so certain materials will give off, like sulfur, will give off very clear wavelengths. So I want to look for sulfur compounds. This is a detector to use. It's specific and it's very sensitive. The other version of this, which I think will be the stopping point, is in this case, we use just a little different way to do the same thing. This monitors the wavelength of light of the flame. So there's a difference between the two, the last one, this one, but they're very, very subtle in terms of differences between them. But sulfur compounds are really important to us. They're exceedingly important to us as flavor compounds. They're very low sensory thresholds and they can be very ugly. So we spent a lot of time looking at this type of detector. Well, wouldn't you know, time's run out. Anyway, I will probably see you Thursday. Go Wednesday. Okay. Graham always sends me notes, Gary. Good to come. Anyway, have a good day.
Well, just enough for the week. If you guys want to hand in your extra credit, what sheet from last week,